Okay, let's dive right in. What could a curveball, a spinning ice skater, and our own planet possibly have in common? I know, it sounds like a weird riddle, but the answer is just this really beautiful piece of physics. Two fundamental types of motion that pretty much describe everything in the universe.
So really, what is that secret connection between a graceful spin on the ice and the silent cosmic dance of a planet? You'd think they're worlds apart, right? But as you're about to see, they're actually playing by the exact same set of rules. It's incredibly elegant.
So here's how we're going to connect all those dots. We'll start with the absolute basics, the two main ways things can move. Then we'll look at something we've all seen, the simple arc of a thrown ball. Before we dive into the really fascinating world of spinning, we'll find out why an object's shape is so important. And finally, we'll take everything we've learned and scale it up, all the way from an ice rink to the entire solar system.
All right, let's get into it. It turns out that even the most complicated movements you see, anything, are really just a combination of two super simple types of motion that are happening at the very same time.
Just look at this throw. The ball is obviously moving forward, right? It's going from her hand to some target. But at the same time, it's almost definitely spinning. And that combination, moving in a line and rotating, that's the key to this whole thing. So let's give these things some proper names. First up, you've got linear motion. That's just a fancy way of saying an object is moving from point A to point B. Think of a car driving down a perfectly straight road. Easy enough. Then you have rotational motion, and that's all about spinning around a central point, or an axis. Like a spinning top or even Earth spinning on its axis.
And here is where physics gets so cool and elegant. There's this incredible symmetry. For every single concept you know from regular straight-line motion, there's a direct cousin in the world of spinning. So, a push or a force becomes a twist called torque. An object's mass, which is its resistance to being pushed, becomes something called the moment of inertia, its resistance to being spun. Even Newton's famous F equals ma has a rotational twin. It's like learning a new language where you already know all the grammar.
Okay, so let's start with the one we're all familiar with, the one we've seen a million times, the path of something that's been thrown, a projectile.
Now, the trick to understanding this path is to realize you can think about its forward motion and its up and down motion is two totally separate things. So once the ball leaves your hand, it just wants to keep going forward at a steady speed. But at the exact same instant, gravity is pulling it straight down, making it fall faster and faster every second.
So what happens when you combine that steady, constant forward motion with that steady downward acceleration from gravity? Well, you get that perfect, predictable curve called a parabola. It's why a baseball, a basketball, even the water shooting out of a fountain, they all trace that same graceful arc through the air.
All right, that covers the straight line part. But now, let's talk about the spin. This is where the real magic is. Because when something is rotating, how much it weighs, its mass, well, that's only part of the story.
We all have a gut feeling for what inertia is. It's just how much an object fights back when you try to change its motion. It's why you have to push way harder to get a car rolling than you do a bicycle, right? The car has way more inertia.
Okay, so spinning has its own version of inertia, and it's called the moment of inertia. This is the big one. It's not just about how heavy an object is, but where that weight is located. It's an object's resistance to being twisted or spun, and it totally depends on how its mass is spread out.
And this, right here, brings us to the big aha moment. Let's look at exactly why an object's shape completely changes the game when you're trying to make it spin. This slide says it all. Imagine all these different shapes, the hoop, the solid cylinder, the sphere. Let's say they're all made of the exact same amount of stuff, so they have the exact same mass. You'd think they'd all be equally easy to get spinning, but nope, not even close. Because their mass is arranged differently, some are a real pain to get rotating, while others are a total breeze.
Let's zoom in on just two of them, a solid cylinder and a solid sphere. Again, let's pretend they have the exact same mass and the exact same radius. Now don't worry about the formulas themselves, just look at the fractions. The cylinder's formula for spin resistance has a 1/2 in it. The sphere's has a 2/5. And since 2/5 is a little bit smaller than 1/2, that means the sphere has a lower moment of inertia. What does that mean in the real world? It's just plain easier to make the sphere spin.
So where do these formulas even come from? Well, the short answer is calculus. What physicists do is they mentally chop up an object, like this plate, into a bazillion tiny little points of mass. And calculus gives them a tool to basically
add up the individual resistance of every single one of those tiny pieces. And the further a piece is from the center, the more it resists spinning. And after all that crazy math, you're left with a nice simple formula.
And this brings us to the absolute best example of this in action, the ice skater. When her arms are stretched way out, her mass is spread out, right? That gives her a high moment of inertia, a lot of resistance, and so she spins slowly. But then watch what happens when she pulls her arms in tight. She's pulled all that mass closer to her center. Her moment of inertia just plummets. And because of a basic law of the universe called conservation of angular momentum, if her resistance to spin goes down, her spin speed has to go up to balance things out. She gets that incredible, dizzying speed just by changing her shape. It's the same thing divers do when they tuck into a ball.
Now for the really fun part. Let's take that exact principle and apply it on a truly cosmic scale. Because the same rule that makes a skater speed up also directs the dance of the planets.
So first, we have to thank the astronomer Johannes Kepler for a huge discovery. He figured out that planets don't travel in perfect circles. Their orbits are actually ellipses, kind of like squashed circles. And the sun isn't right in the middle. It's off to the side at one of 2 points called foci.
And that weird elliptical orbit leads to something amazing. Kepler realized that a line drawn from the sun to a planet sweeps out an equal amount of area in an equal amount of time. Now, what that actually means is that for those two shaded areas in the diagram to be the same size, the planet has to travel way faster when it's closer to the sun. Sound familiar? Just like the skater pulling her arms in, the planet is reducing its distance from the center, so its speed has to increase. It is the exact same physics.
But what's the invisible string holding the planets in these orbits? Well, of course, it's gravity. It was Isaac Newton who finally gave us the why. His law of universal gravitation described that constant pull the sun has on the planets, the force that keeps them from just flying off into deep space and locks them in this cosmic dance.
So isn't that just incredible? The very same rules that let a skater accelerate into a blur are also the ones guiding the planets on their journeys across billions of years. The laws of physics don't care if you're on a frozen pond or floating in the void of space. They are truly universal.
And it really makes you wonder, doesn't it? If the physics behind a little spinning top on your desk and a whole spinning galaxy are one and the same, what other incredible universal connections are just hiding all around us, in plain sight, just waiting for us to notice?